Okay, let me get started. Today is mercifully the last class of the semester. We are, just to remind everybody where we sit. Yeah. Okay, so today, I guess, as of midnight tonight is when homework 5 is due. If you have an extension still surviving, turn it in up to a week late there. Okay? Any questions about homework 5? Okay. Then what else do we have? We have a final exam coming up. What are the details on the final exam? I believe the final exam is December 14th. Is that correct? And I believe it is at, what day of the week is that? What? Tuesday. Okay, and it is at like 2 p.m. if I remember correctly. You should look it up to get an official word, okay? What should you expect? It will be just like the midterms, except more so. Okay, it will have, instead of 3 problems, it will presumably have 5 problems. And instead of having 30 multiple choice questions, it will have more. I don't know, maybe it'll be 50, maybe it'll be some, maybe, I don't make a promise. But it will scale sublinearly in the amount of time that we had so far. So if you're able to complete a midterm, you should be able to complete the final in the allotted time. Any questions about that? As far as the problems, the only thing I'm going to guarantee you is that there will be 1 written problem on NP-Completeness. So it's good to try to figure out how to do that, but the other 4 problems will be from somewhere of what we did this semester. How should you study for the final? An excellent thing to do is to go back and look at the homework problems. Make sure that you understand how to do, not that I'm just going to be including the homework problems, I don't have any explicit intention of doing so. But I think that these are the kind of problems that the written parts will be drawn from. Okay? Give it a shot to understand the things that you didn't understand before. Any questions about that? Any other questions about the final? Okay. If so, then what I'd like to talk about today is NP-Completeness for one last time. And again, where do I have my, actually, I thought I had, where did I have my, oh, I don't have it here. So I'm going to make sure I load it up, because I promised I was going to show you the same set of slides every class. What is the idea behind NP-Completeness? Hopefully by now this will sink in, and maybe that now what seemed like a mystery when we first saw it will be clear. What is the problem? We are giving an algorithm, okay? Suppose I have an algorithm to solve the Bandersnatch decision problem. Remember, Bandersnatch is a yes-no problem. The input for Bandersnatch was G. This algorithm works by translating the input of G, okay, into the input Y of a problem called Bobili in such a way that Bandersnatch of G is equal to Bobili of Y. Bobili is a yes-no problem, okay, or a true-false problem. Bandersnatch is a yes-no problem or a true-false problem. For them to return the same answer, for Bobili of Y to equal Bandersnatch of G, simply we need to know that when Bandersnatch of G is true, Bobili of G of Y is true, and Bandersnatch of G is false, Bobili of Y is false. Okay? If they have the same answer, okay, then we can return the answer to Bobili of Y as the answer of Bandersnatch of G, and we have a correct algorithm. Okay? What is the implication of this? There are two possible implications of this Bandersnatch algorithm. If my translation is fast, running in polynomial time, and if Bobilli has a fast algorithm running in polynomial time, maybe my translation takes n to the 5th and my Bobilli takes n to the 19th. Okay? This will give a polynomial time algorithm to Bandersnatch that basically takes the cost of translation plus the cost of Bobilli. But if instead we have a guarantee that Bandersnatch cannot be solved in polynomial time, okay? If we know that there is no polynomial time algorithm for Bandersnatch, an algorithm like this means that there is no polynomial time algorithm for Bobilli. Because if there was a polynomial time algorithm for Bobilli, this would be a polynomial time algorithm for Bandersnatch, and there is no such thing as a polynomial time algorithm for Bandersnatch. This is how we are proving that Bobilli is hard. Any questions about this logic? Okay. Any questions about what the two implications are and how we are going to use this idea to prove that problems are hard? Okay. Any questions? Okay. Let's go and look at what you call it, the problem of the day, which I think is over here. Where's the problem of the day? Kabunk. The problem of the day said the hitting set, talked about the hitting set problem. What is the hitting set problem? You're given a collection of subsets, okay, of a set S. So let's say that there is this, S is this universal set of things, okay, maybe the numbers 1 through n, okay, and C is a collection of subsets, 1, 5, 9, 2, 7, 3, 2, 7, okay, 3, I don't have them in order. You see what I mean. I'm giving you collections of subsets. 2, 7, 6. Okay? And what we want is a small, if these are my subsets, we want to know, find me a subset S prime of S that's small, meaning it has only k elements, such that every subset in C has at least one of them. My claim is that I could cover these three sets with two representatives. Does everybody see that if I have you the sets 1 and 7, 1 is in the first subset, 7 is in the second subset, 7 is in the third subset. If I pick the elements 1 and 7, those take care of the, those hit each of the subsets that were given. We're looking for a small number of elements such that every subset has at least one representative. Can anybody think of an application for such a thing? Or why would anyone care about a hitting set problem? Okay? You might imagine a world where, let's say that we wanted to form a committee of students to represent the entire group of students, the entire student body. Some of you are male, some of you are female. Some people are engineers, some people are in the College of Arts and Sciences, Some people are a member of the Crips gang. Some people are a member of the Bloods. Okay? Some people here are Jewish. Some people are Christian. Okay? Now, if I wanted to come up with a representative, I want to make a set of representatives. I want every one of those every one of the different demographics to have a representative on the committee, right? Does that kind of make sense? What would be the ideal representative? If you could give me a woman, Jewish, Crip, engineer, okay, who's double majoring in the college, okay? Does everybody agree that you want one person to cover as many demographics as possible? If we want to have the smallest representative committee such that every sub-demographic has a representative, at least one representative on the committee, we're asking for a hitting set problem. Any questions about the hitting set problem? Where that comes in? Okay? Fair enough. How do we prove that the hitting set problem is hard? Okay? We need what? We need a Bandersnatch and a Bobilli. Okay? Does anyone want to propose what is a Bandersnatch? A Bandersnatch is a problem that we know is hard, that we think is going to smell like the hitting set problem. Which one do you want? Vertex cover. Okay? Why do we say vertex cover? Well, first, let's say philosophically, why do you say vertex cover? Okay, what I'm hearing you say is in vertex cover, you want a small number of vertices to cover every edge. Is that what vertex cover is? So what is this thing being like? You're telling me that Bandersnatch is vertex cover. What is Bobilli? Hitting set. Actually, sorry, I didn't write that very neatly. And what is the input? The input is a collection of C subsets on a set S and a bound, let's call the bound K prime. If you're going to be giving me a translation, you need to tell me what is C equal to, what is S equal to, and what is K prime equal to. How do we transfer hitting vertex cover into hitting set? Okay, thought I saw a novel hand up there before playing it out. What do you do?
Collection is the set of edges represented by...
So this is going to be the set of edges in the graph. So let me just think about it. You're going to tell me that let me just think about it. You're going to tell me it's the set of edges. Why don't we first think the S is built, the C is built on the S, right? What is your S going to be?
The set of vertices.
Okay. You're going to tell me that's V1 dot 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 Vn. So this universal set is going to be the set of vertices of the graph. Now, what are my collections going to be?
Their edges represented as the two endpoints.
So you're going to tell me each committee, each demographic is going to be represented by a subset of size 2. Is that right? You're going to tell me that there is the edge 1 demographic, which has some vertex VA and VB. The second edge was going to have one V and another V. Do people see what we're doing here? Each one of our subsets is going to consist of two vertices. Okay? Namely, the two vertices that define each edge. Right? Now, what's that mean? A hitting set says, give me a small, and what's K prime going to be? What does this mean? This says you want to find a vertex, a hitting set is going to be, find me a small subset of the elements of S of size K prime, okay, which is K of the original problem, such that every one of these two-person sets has at least one vertex in it. That is exactly what the vertex cover is doing, isn't it? Okay, what was our vertex cover? If here, let me make up a graph. Let's say something like this. Here I've got vertices 1, 2, 3, and 4. What are the, so my universal set here would be 1, 2, 3, and 4. That's my S. You can see that, right? Or no, you can't see that. Yes, you can see that, right? You get that part of the board. And what are the subsets I'm getting? I'm creating the subset 1, 3, 2, 3, 1, 4, 1, 2, and 2, 4. What is the vertex cover of this graph? What's the smallest vertex cover of this graph up here? What is the smallest vertex cover of this graph? Okay, it's important to know what vertex cover is. What's the smallest vertex cover? How big is it? 2, what are the vertices? 1 and 2. If I take vertices 1 and 2, okay, then what happens? Then every one of the edges is kissed on this. One edge is kissed twice, right? And what do I know if I take 1 and 2 as my hitting set? I hit this, I hit this, I hit this, I hit this, I hit both of them, I got that. Every one of my 5 committees of 2, my 5 demographics of 2, gets hit by a representative of the committee. Any questions about that? Okay. This kind of shows that once you have enough problems that are, you know are hard, that are Bandersnatch candidates, often you can find a good match between the Bandersnatch and the mobility. Yes?
The hitting set is a vertex cover, right?
So in this case, the hitting set, remember, well, vertex cover, remember we did a translation, okay? Remember, vertex cover was a problem on a graph. Hitting set is a problem on a set of elements, right? Now, it's not clear that when you say something is a something, I think it's fair to say that every element in the hitting set problem represents a vertex in the original graph, as opposed to being is a vertex of the original graph, right? Was that your question?
No, the output for the hitting set, the elements and the...
In this case, the hitting set is 1, 2, and the vertex cover set was V1, V2. But notice that because these are decision problems, for this thing, is there a hitting set of size 2? The answer is yes. That's because there is a vertex cover of size 2. Remember, these are decision problems. Any questions about this reduction? This is the kind of reduction that I would say is a fair game for the test. Any questions about that? Yes? Well, but the idea of the edges, remember, what are we doing? We're translating, in this case. We want to find the vertex cover of a graph. Do you agree that this is a graph and that those two blue circled vertices are a vertex cover of it, right? That is a graph question. If I ask, does this graph have a vertex cover of size 2? The answer is yes. If I say, does it have a vertex cover of size 1? The answer is no, right? Now, I am giving you an algorithm to tell me whether a graph has a vertex, a specific graph has a vertex cover of a certain amount of size. By translating that graph into a set, some sets, then calling the hitting set problem on it. Okay? If this system of sets has a hitting set of this size, then this graph has a hitting set of that size. Okay? So I don't know if I've answered your question. What's your question again?
And so then, like, for example, for C, the first element is like E1, E2, would that mean that there's element, like a number in common between the two subsets of E1 and E2?
Okay, so I am doing a translation. Recognize that what this is doing is a translation, right? Hitting set is expecting something in set language. Does everybody agree this is a problem in set language? Okay? And this is a graph in vertex cover language. Okay? I did my translation, and I did it in a way that I am going to call what used to be vertex 1 is going to correspond to the element 1 here. What used to be vertex 2 is going to correspond to the element 2 here. Right? Now I've got a legal hitting set problem, and this thing will have a hitting set of size k if and only if this graph has a vertex cover of size k. Does that answer your question or not really? How am I making the edges? The edges are given to me. You see, this is a subroutine for solving vertex cover. So the input to the input instance was the graph, a graph and a size, right? And if you want to tell me, does this graph have a vertex cover of this size? I'll say, I'm going to translate it bloop, 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 into a hitting set problem, and I'm going to call my hitting set solver. If I have a fast hitting set solver, that would give me a fast algorithm for vertex cover, but we know there is no fast algorithm for vertex cover. So really this would show me that there can't be a fast algorithm for hitting set, because if there was, this would have given me the impossible fast algorithm for vertex cover. Any questions? Actually, I just realized I didn't put on the magic horrible mask. Let me just try that. Actually, I'm going to have a ceremony burning this mask right after class today, so I don't have to use it again. Okay, any questions about that? Okay, any questions about the problem of the day? Okay. Okay, what I'd like to now do, I think that if people got that, right? Any questions about the problem of the day? Okay, what I'd like to now do is complete my coverage of of NP-Completeness by kind of giving you more ideas as to how you find these kind of reductions. If you look at these reductions, hopefully you can convince yourself that they're right. Okay? It may seem like a miracle. Where did these reductions come from? Okay, like that, especially the hard one we saw was going from 3-set to vertex cover. That looked like a weird thing. How does a human being find that? And so I'd like to talk a little bit about the art of proving problems hard. Okay, kind of what is the idea sequence here? Okay? And generally in this class, or the kind of, let's say, reductions it doesn't require a wizard to do, there are kind of two different kinds of things that happen. Often, okay, there's what we would call a way to prove that your problem is hard is what we would call restriction. Namely, show that there's a special case of your problem that is NP-complete. At some point in this semester, the other day, I told you that set cover was NP-complete. I don't know that I ever actually drew one of these little algorithms or flowcharts to pseudocode things to prove it. But why was the set cover problem that you guys did on your homework for, why does that have to be hard? The reason is we know that vertex cover, okay, is an NP-complete problem, right? And vertex cover, every vertex you had covered a certain class of edges. Vertex cover was pick every example, find the smallest number of vertices, such that the union of their neighborhoods is the complete set of edges. Every vertex cover problem is a set cover problem. Not every set cover problem is a vertex cover problem. Okay? But we know that the vertex cover problems alone are hard. Since set cover is a generalization of vertex cover, set cover has to be as hard as vertex cover. Any questions about that? That, I think, if you understand the logic, that's not so hard. The other idea in proving things hard is usually maybe there's ways of making local changes or local translations of the structure. Okay, this is what we did when we were proving that 3-set was hard. Okay? Any questions? Okay. Now, once you get the hang, proving things NP-complete looks like a really challenging thing. If you get enough practice at it, like anything else, okay, it becomes not that hard to do. Often a lot of these NP-completeness reductions are easy to do. And the reason has something to do with the fact that it's easier to rewrite code than it is to read something. Okay? I don't know if any of you have ever had a job of looking at somebody else's code and modifying it to add features? Now, what did you do? You probably looked at this diseased code and you said, I don't understand it, and you threw it away and rewrote the whole thing from scratch. Is that the way it works in software engineering? Okay, hopefully your software engineering teacher will tell you something different. But in practice, that often is the case. It's hard to understand somebody else's logic. And when you're looking at reading these NP-completeness proofs, you're looking at somebody else's logic, okay? That kind of, when you looked at that 3-set to vertex cover reduction, why did he set it up as triangles? And why did he connect these things? And he could have done it in different ways. Okay? That's just one way. That's just the program that they wrote to do that transformation. There often are other ways to deal with it. Okay? And so when somebody comes to me and tries to when I have to try to understand somebody else's NP-completeness proof, I usually throw it away and start from scratch because it's easier to kind of do your own code rather than understand somebody's. Okay? That said, let me tell you how I go about proving things hard. Okay? The first thing to note is that you want your Bandersnatch problem to be as simple a problem, a hard problem as you can. Remember that you have, what is it, Bandersnatch? You've seen this before. Bandersnatch is getting translated into Bobilli. We need Bandersnatch to be a hard problem, or else we're not going to be able to prove Bobilli is hard. But we want it to be as simple a hard problem as we can, because we want to have to translate every single possible instance of the Bandersnatch problem into something else. The more restricted, the simpler it is, while still being hard, the easier it is to do that translation. That's why we like 3-SAT very well, okay? 3-SAT is better than satisfiability for us in general. Why? Because it's a simpler, hard problem. Okay? Any questions about that? Some people, when I talk about Bobilli, I say, give me a Bandersnatch. People often will come back and say, oh, traveling salesman problem. Everyone knows the traveling salesman problem is hard. I have never, as far as I can tell in my life, used the traveling salesman problem as a Bandersnatch. Why? It's too complicated. What would be simpler? Traveling salesman problem, you can have any weights on any edge, right? What would be simpler than traveling salesman? What happens if I insist that the edges satisfy the triangle inequality? That if I have vertices A, B, and C, that the distance from A to C is less than the distance of A to B plus B to C. That's a smaller set of problems than all TSPs, right? So it would be simpler to translate from that. Even simpler would be to just use Hamiltonian cycle, which is assuming an unweighted graph. I'm given a graph where the weights are basically each edge has a weight of 1, or there's no edge between certain pairs, and that has a weight of infinity. Hamiltonian cycle says, is there an ordering to visit all the vertices, okay, without repeating any one, right? That's sort of like a TSP. It's a TSP on a graph with these special weights, okay? But this is simpler, right? So I like that better. I use Hamiltonian cycle fairly often. Actually, I often use simpler versions of things. Hamiltonian path says, is there a path that connects all the vertices, okay, without repetition? Doesn't have to come back to where it is. Finding a Hamiltonian path is a hard problem. Maybe that's easier than having to connect it. Actually, Hamiltonian path on a directed planar graph where each vertex has total degree 3 turns out to be NP-complete. So if I really need to, I can use this version. Is just as hard as this version, but it's easier to do the translation. Any questions about this philosophy? I want the simplest hard problem to translate. Okay? Any questions? Okay, yes.
For the final, which NP hard problems are we allowed to use?
Okay, so which NP hard problems are you allowed to use? You are allowed to use, okay, what I will tell you is I will probably, first of all, if I give you a hint and say translate from this, I would recommend you take me up on my hint, okay? If not, the problems that we've talked about in class are fair game. But how do I choose these? Well, we'll talk a little bit more about that. How do I choose them in general? But I think the ones that we've talked about in here are fair game. Okay? Any questions? Okay, what else can you do to prove it hard? If you want to prove a problem hard, remember, mobility is the problem you're trying to prove hard. How do you make, if you want to prove mobility is hard, how do you make your task easier? The harder and more general, the more general mobility is, the harder it probably is to solve quickly, right? Should you use, let's say you have a particular mobility problem. If you can't figure out how to prove a reduction to mobility, what about weighted mobility? In the original mobility problem, maybe every thingamabob had constant weight. If I allow the freedom of setting different weights, the problem's more general, right? The mobility solver is more powerful. Okay? If I want to do this reduction, I want to make my mobility problem as hard as possible. Directed mobility, weighted mobility, weighted directed mobility, hyper-weighted mobility, or whatever you make it more complicated, it is potentially easier to use to prove it's hard. Then once I have proven my souped up hard problem hard, I will then see if I really needed the souped upness to do it. Usually I can then get rid of it. But sometimes I need to do this. Like for example, I'll have you know this morning, there's a problem Joe Mitchell and I and some other algorithm faculty have been batting around trying to prove it's hard. And I think I got it this morning. And the way that I got it was actually using this. There was a problem on a string. Okay, a text string. And it was, that I wanted to prove hard. And instead I was able to prove that if you give me not one string, but you allowed to break the string into pieces, so the input is not one string, but a bunch of strings, this version of the problem is hard. Okay? It captures the flavor of the original thing I wanted to prove. Once I prove that the one on many strings is hard, then it's probably relatively short work to go back and figure out how do I stick these pieces together into one string. That's exactly what I'm trying to do here. Okay? Any questions about that? Okay. What else is that? How do I select the right starting problem? Okay, that's kind of the question that you were asking. Okay? Now, different people probably have different strategies. Generally speaking, I almost always use one of 4 kinds of problems as my Bandersnatch. Okay? If nothing else works, I go back to 3-set. Theoretically, 3-set will work for anything, by the way. If it can be done, it can be done from 3-set. Okay? But, sometimes that's necessary. If I'm dealing with a problem that requires large numbers, there's a problem which I didn't talk about, was on the slides from last time, called integer partition. What is integer partition? Integer partition is, I give you a set of numbers. Let's just see if I can do it here. Let's say 9, 10, let's say 12. And I ask myself, is there a way to break this into 2 subsets that add up to the same thing? Okay? So what's this thing? What's the total here? 1 plus 3 is 4. 4 plus 7 is what? 11. 11 plus 9 is 20. 30. 42. Does everybody agree the sum of this is 42? Somebody check my math here, because this is complicated. Does everybody agree that the sum of those integers is 42? Half of 42 is 21. Is there a set of those numbers that adds up to 21? Okay. Is there a subset of numbers here that adds up to 21? I see some nodding. Which ones add up to 21? 10, 7, 3, 1. 10, 7, 3, 1. That adds up to 21. And notice the other half adds up to 21 too, right? The integer partition says, is there a way that I can partition the numbers into two equal pieces? Okay? Sort of like if I was making a tug of war team. You guys know the game tug of war? You have two teams of brutes on a rope. Okay, there's a rope. Okay? And you have a bunch of people on one side of the rope and a bunch of people on the other side of the rope. And these people are pulling back and these people are pulling back. You would like it to be the winner is the one that pulls the other team away, right? To make tug of rope fair, you want both teams to have the same amount of weight on each side, right? Integer partition is the problem of how do I make a fair tug of war team from a bunch of people given their weights. This problem is a hard problem. Okay? So I know about set. I know about integer partition. I know about vertex cover and all of its close relatives. Okay? And I know about Hamiltonian path. Hamiltonian path is good, or Hamiltonian cycle. These are graph problems associated with ordering of vertices. Vertex cover is associated with subsets of vertices. If I have a problem involving subsets, I think vertex cover. If I have a problem on ordering, I think Hamiltonian path. Any questions about that? When I think about doing these things, again, now it gets kind of philosophical. I try to think in terms of trying to translate the problems while making them stay kind of the same. That's kind of the important thing in a translation. You guys were saying, oh, when I translated it, was it the vertices or was it the vertices or that are translated the same? I translated a vertex vi into an integer I. Okay? So I needed an integer here, but I kept the kind of correspondence. I want to keep the problems the same as much as possible. Okay? And, you know, when you think about this, you kind of want to show that the good things to do with the original problem are the good things to do in the translation. And the bad things to do in the original problem are the bad things in the translation. That's kind of the idea here. That may be more nebulous than some of the other things I said. The other thing is when I do these translations, thinking of what, in units that I guess people call a gadget. What is a gadget in real world? If you said, what is a gadget? Do any of you have gadgets? What is a gadget? Okay, what does the word gadget mean? It's kind of a little machine that does something, right? Or a unit of a machine that does something. I want you to think in terms of how do I build parts out of the problem, okay, that kind of do what I want, okay? How can I build parts of my graph so that vertex A is chosen before vertex B? How can I make sure that either you're going to pick both, either A or B, but not both? Okay? These are the kind of thinkings that I like to do when I'm, building these things. Okay? And again, this is also nebulous, but maybe once you see more of them, it makes sense. And finally, I encourage people to alternate between, if you're trying to solve a problem, and you're trying to find an algorithm for something, and you can't find the algorithm for something, then think about trying to find an NP-completeness proof for that problem. And if I can't find an NP-completeness proof, then I go back to thinking, well, maybe maybe I can't find an NP-completeness proof because the problem isn't hard. Maybe there is a polynomial time algorithm. And so moving back and forth, after you think about the hardness for a while, it probably gives you some ideas that might lead, when you know why it isn't working, it may tell you, think about why there's a fast algorithm for it. Any questions about these? This is life wisdom, maybe a little too early for some of you, but just, you haven't done too many NP-completeness proofs in your life. Any questions? Okay. What I'd like to do now is I'd like to give myself the NP-completeness challenge, which is always what I like to do. I am going to tell you that finding NP-completeness reductions, once you know what you're doing, usually it's not so complicated. There's a logic to this. So what is this? This is one of my favorite books. This is a book by Gary and Johnson, which at the time it was written, listed every single NP-complete problem known to man when this book was published. Actually, this was published a long time ago, so they only have like 300. There's probably now tens of thousands of problems that people have proven hard. But these are kind of important ones. So I want you guys to pick out a random problem for me, and I'm now going to try to come up with a reduction as we watch it, and let's see if we can do this, okay? So what is the story? The problems, I once went through the book and picked out the problems that I think people could understand. They're graph theory problems, network design problems, set and partition problems, storage and retrieval problems, and mathematical programming problems. Okay? Which type of problem do we want to see? I want everybody to vote. Pick a category here. Okay? Who wants to see a graph theory problem? Seeing a fair amount of twitching. Okay? Who here wants to see a network design problem? Similar twitching. Who here wants to see a set and partition problem? Okay, I am actually seeing more twitching. I'm not sure I'm happy about that, but who wants to see a storage and retrieval problem? I think I am seeing less twitching. Who wants to see a mathematical programming problem? No one. That's not a surprise. Okay, I'm hearing set and partition problem. That's what I think what the majority was. I need a volunteer. You. I want you to now pick another volunteer. Pick a volunteer.
They have to raise their hand.
Or they'll hate you for life. Someone be a volunteer.
I pick you over there.
Okay, you. Whoever was the volunteer. Who got picked? The gray shirt. Okay, you pick a number, one of these numbers. Which number is it? 8? SP8. What is an SP8 problem? Okay. Let's see if we can do this one. Actually, hold on. Sorry about this. I'm getting a little carried away. SP. Sorry about this. Network design. Where is this? You won't believe what SP8 is. It says hitting set. Okay? So I'm going to let you pick the other guy. You didn't do a good job then. You pick a different one. What? SP12. Okay. SP12 is actually the one that, interestingly, it looks like this is integer partitioned. Okay? let's, I mean, we could try to prove this. Wait, this one I know how to do because this is the one that was on the slides from last time, which I didn't go through. Let's try a different one, okay? Any other one here? You know, this is less impressive here. Let's try one more, and if we'll then give up. What? 3. SP3. Oh, okay, this is interesting. And this one's going to be a hard one for me. This one is called, in fact, this one I don't know how to do, actually. So let's try to figure this one out. This one is called set packing. Let's try it like that. This is called set packing. Okay, this one I'm getting myself into some trouble with, I think. I may have gotten a little too cocky here. Okay, what is the story of set packing? Okay, first I can't write it. Hold on. What is set packing? Set packing says that I am given a collection of sets on some universal set and a bound K, and I want to know, does it contain K mutually disjoint subsets? Actually, okay, so what am I going to be saying here? I want to know, does this collection of sets contain K mutually disjoint subsets? Okay, let's think what that means. So suppose my subsets were 1, 2, 2, 3, 3, 4. Okay, sorry. And let's say 4, 5. Let's say 4, 5. Let's say 4, 5. Are there are there two mutually disjoint subsets? Okay, meaning that they don't contain any elements in common. This and this is a set of two subsets which have no elements mutually in common. Does everybody agree with that? Okay. What about this one? These two contain no elements in common, right? Does everybody agree that in this case for K equals 2, the answer is yes. For K equals 3, the answer is no. Okay? Any question about what the set packing problem is? It's kind of, in this case, I want to find a world where, if we picture a world where there's different subsets of communities, each one of these is a constituency. I want to find, are there K constituencies whose union has no, where there's no intersection between it? Okay? The Crips and the Bloods shouldn't have anybody in common, if we understand gangs the way that I understand them, right? So the Crips and the Bloods would be independent, okay? The question is there an independent, a set of independent such things, such that it adds up to K? Okay? Any questions about the problem? Do we see how to do it? Okay. Now, what am I going to be trying to think of a reduction? What problem is this like? Okay? Well, there is a problem on graphs that this is sort of like. Okay? There's a problem of finding a large matching in a graph. Okay? You know about matchings in graphs? Given a graph, okay, there's a graph, right? This graph has 1, 2, 3, 4, 5, 6 vertices, right? Now, if every one of my collection of sets was an edge, what is this problem asking for? Is there a collection of a set of edges such that they don't have any vertex in common? Does everybody agree with that? This problem of finding a matching, okay, they call that a matching in a graph, right? Does everybody see that a matching, if I could solve if matching was hard, set packing would be hard. Does everybody kind of agree with that? Any questions? The trouble is, in fact, matching turns out to have a fast algorithm. Okay, so that's not enough to prove that this problem is hard. But you see how the mind is working? Okay. Any questions about it? Okay. Now, which of the problems we have looks most like set packing? Yeah? Independent set. Let's think about independent set. Independent set in a graph means what? An independent set was a collection of vertices, okay? Actually, here's an independent set. I don't know, is there one bigger? An independent set was a collection of, a collection of vertices such that the edges that they are on is not, basically not in common with each other. Does everybody kind of see that? Does this sound like what we're doing here? This is starting to sound very good to me. Why is this sounding good to me? What am I going to be saying? I think I want to say maximum independent set on a graph G with size k bound. I want to use it to solve set packing, where I'm given a collection, a universal, and a k prime. What is going to be my thing? In set packing, I want subsets, and I want each pair of subsets to have nothing in common. In independent set, I want a set of vertices such that none of the edges that kiss them are in common, right? So what am I going to do? I am going to claim for my universal set is going to be E1, E2, up to EM. Each edge is going to be an element. My collection of sets, C, is going to be the union over all I of Ci, where the ith collection is going to, maybe I'll just do it, let's not simplify it. I'm going to say for each vertex, vertex I, what am I going to say? C of I is going to be equal to all edges of the form, basically all x, such that there is an edge ix. Okay? Maybe I wrote this clumsily. It's easier for you to hear what I'm saying in English, right? It's going to be the set of all the edges that are incident upon vertex I, right? And then k is equal to k prime. K prime is equal to k. Do people follow what this reduction is? Let's go back and look at it again. What am I doing in this translation? Here was my graph. Let's go do this translation again. What is it saying? I don't remember. Okay, let me draw a graph. Okay. Let's say I've got a graph. Vertex 1, 2, 3, and 4. Does everybody agree? What is the maximum independent set in this graph? How big is it? What's the biggest independent set in this graph? 2. What am I now going to translate this to? I'm going to call my edges, let's call them E1, E2, E3, E4, E5. My universal set is going to be E1, E2, E3, E4, E5. Does everybody agree? What is my collection going to be? Well, first I got to think what's neighboring on vertex 1. On vertex 1 is E1 and E2. What's bordering on vertex 2? I've got E2, E3, E5. What's bordering on vertex 3? Vertex 3 is going to say, vertex 3 is going to be on E4 and E5. And vertex 4 is going to be what? E1, E2, E3, and E4. Can you find two of these sets? Let's say that we ask, is there a vertex cover of size 2 in this? The answer was yes, that and that. Are there two subsets here such that they are disjoint? Which two subsets are disjoint? The ones that correspond to vertex 1 and vertex 3. Right? Does everybody see that? If I had a fast set packing thing, does everybody see that with this reduction, if I had a fast set packing algorithm, this translation takes time linear in the size of the graph. I could build this translation easily. If I had a fast set packing solution, what would that do? This would give me a fast maximum independent set solver. But can there be a fast maximum independent set solver? There cannot. So that means that there is no fast set packing solver. Okay? QED, end of the story. Okay, set packing is hard. Any questions about that? Do people see how we went about this logically? Again, the student came up with the key idea here, right? Okay? Any questions about it? I like doing these NP-Completeness proofs because it's like you're changing forms. You're putting one problem in disguise for another problem. That's what you're really doing. Okay? And I like this kind of thinking process. Any questions about how we proved that set packing is NP-complete? Any questions? Going once, going twice, sold. And once you've done it, you'll see that this isn't that complicated. That's the important point here. Any questions? Okay. Let me try to erase this. Hold on. Okay, what I'd like to now talk about are some of the philosophical implications of NP-completeness. Because NP-completeness, we've seen it, it's a useful technique to prove that algorithms don't exist. But there's some, kind of deep things and language for this that you may have heard of. This looks like too hopeless here to erase this thing. I'm going to leave some graffiti on my screen. Okay. Many of you, I hope, have heard of the question, is P equal to NP? Right? This is kind of a famous thing in computer science. The most famous problem in computer science is P equals NP? And any educated computer scientist should know what that means. What does that mean? Well, what is P? We've seen that we can talk about problems like the traveling salesman decision problem, or the shortest path decision problem, or any algorithm problem we've talked about in this class is a problem. You can convert it into a yes-no question in a way that preserves what its meaning is. A decision problem is in P if you can solve it in time polynomial in the size of its input. Is there a shortest path of a certain size between A and B? That problem's in P because it's a fast algorithm. Is there a minimum spanning tree of a certain size? That problem is in P because there is a fast algorithm. P is the set of problems we know how to solve quickly. We have fast algorithms for. Fast algorithms to solve them. A problem is in NP if we can check the answer. If we're given the answer, we can check it quickly. Okay? If we're given the answer and enough auxiliary information about the answer, we can check the answer quickly. Now, if I give you this graph, this is a weighted graph, and I tell you that I give you a tour, vertex 1, 7, 3, 2, 16, ... I give you an order of the vertices. And I tell you that this order of vertices is a TSP tour of length less than or equal to 100. Could you check that out quickly? If I give you the tour, and I give you the graph, and I say, is the TSP tour, is this tour of weight less than 100? Does everybody agree you could check the answer very quickly? Just go through the edges. What's the weight of the edge from 1 to 7? Add that to the edge of the weight from 7 to 3, to 3 to 2, to 2 to 16. Checking the answer, if I give it to you, is easy, right? If I say this graph has a TSP tour of length, less than 100, and here it is, you can check if I'm right, okay, quickly. Problems you could check the answer for quickly are an NP. Problems that you could solve the answer without anybody's help quickly is in P. Okay? Is every problem in P in NP? Suppose I know how to solve a problem in polynomial time, and someone then asks me to check it. Here's the answer. Can you check it quickly? Hell, I can solve the problem. I don't even need your answer to tell you yes or no whether it can be done, right? I can solve it from scratch, okay? So every problem that is in P is in NP. If I can solve it quickly, if you now give me the answer, I can still solve it quickly, right? It doesn't make it any harder for me. The question is, are there problems where you can check the answer quickly but not solve them? That's what the P equals NP question is. Okay? Is it true that if P is equal to NP, okay, if P equals NP, then any problem that you can check the answer to quickly It would mean that you could solve it quickly. Okay? If P is not equal to NP, then there exists some problems, hard problems in NP, that you can't solve in polynomial quickly. Okay? Satisfiability would be the candidate for this, right? If satisfiability, if I give you a satisfiability problem, and I ask you, I say, okay, here's a satisfiability problem. I say that if you set the variables v1 to be true, v2 to be false, v3 to be false, I say this satisfies the equation. Could you check if I'm right quickly? Certainly, you just plug it in. This, or this, is it true? Yeah. This, or this, is it true? Yeah. All the clauses are true. The and of all the true clauses is true. Okay? Checking it is easy if I give you the answer. Okay? Satisfiability is in NP because it's easy to check if somebody gives you the answer. It would be in P if it was easy to find the answer. Okay? Right now we know that satisfiability is in NP. If P is not equal to NP, then satisfiability is an example of a problem that would be in NP but not in P. Any questions about it? Okay, so that's when people are talking about P equals NP. This is what people are talking about. Any questions? Does anyone know what NP stands for? P stands for polynomial. What does NP stand for? Does anyone know? What should it stand for? What? Not polynomial is what it should stand for. Turns out it stands for non-deterministically polynomial for reasons that are unimportant to me right now. But the answer is you'd think about it as not polynomial. Okay? That I think is the right answer here. Any questions? The hard part about NP, about the issue about is P equal NP is finding answers harder than checking answers. Okay? Is it harder to find the proof of something or to check somebody else's proof? Okay? Those of you who are planning on copying somebody's answers on the exam, you're kind of banking on the fact that it was hard to come up with the answers, or else you would have come up by yourself. But it's easy to check if the guy next to you had the right answer, right? You wouldn't want to copy his answer if it was wrong, would you? Okay? Again, we're not copying answers on the final. That's not supposed to be the lesson here. It's supposed to be the difference between checking and verifying. Any questions? So what is interesting about this? And then I will turn it over to you. Okay? There are problems that we've seen that are in P, like shortest path. There are problems like TSP tour that are known to be in NP because we can check it quickly. There's even harder problems, by the way, that are not in NP. Okay? If you get fancy, like if I ask you how many TSP tours there are, okay? You can't write down all the tours. There's an exponential number of tours. To look at all of them would be hard. Okay? So there's even harder problems. But again, I don't want that to be confusing you. Okay? The main thing is that I'm interested in is we can use reductions to show whether our problem is hard. Okay? The amazing thing about algorithm design, one of the ways to see how good a field algorithm design is, almost all interesting problems people have come up with for there being algorithms, either you've come up with an NP-Completeness proof, which suggests that there is no fast algorithm for it, okay? or people have a fast algorithm for it. And there's only two problems that are really kind of things you guys could understand that people really don't know for sure, one way or another, whether there is a fast algorithm or no fast algorithm. Okay, it's kind of amazing. Factoring integers turns out to be one of these things. Okay? Factoring integers, no one knows for sure if it's really, really hard to factor integers. In fact, you can do it on quantum computers, supposedly, so there's a kind of a weird thing there. And telling whether two unlabeled graphs are the same. Probably both of these problems can be solved in polynomial time with enough, or else, neither of these are probably hard. They're probably in a little bit of a limbo between P and not NP. Any questions? Okay. And certain problems, it's interesting because certain problems, finding the shortest path between two nodes in a graph, that's polynomial. Finding the longest path in a graph, that problem is NP-complete. Finding the smallest set of edges that covers the graph, that was that matching problem I told you about at the beginning when I first started to do this reduction for set packing, right? That's as a fast algorithm. Covering the vertices with the smallest number of vertices, all the edges with the smallest number of vertices. That one's hard. Somehow the world is broken into hard problems and easy problems. And so what is the state of this problem? Is P equal to NP? I told you that satisfiability is hard, right? And there is a lot of evidence for that satisfiability is hard. It is 100% true that no one in the world knows a fast algorithm for satisfiability. It is 100% true that if somebody came up with a fast algorithm for satisfiability, there would be a fast algorithm for everything in NP. Okay? If you come up with a fast algorithm for satisfiability, you get a fast algorithm for TSP, you get a fast algorithm for vertex cover, you get a fast algorithm for everything else, which is another good reason to believe that satisfiability is hard. That said, no one has ever really completely rigorously proven that P is not equal to NP. I believe P is not equal to NP. Joe Mitchell believes P is not equal to NP, I'm sure. Haven't asked him, but he'd believe that. Okay? It's almost certainly the case that, and certainly from my assumption as an algorithm designer, I say P is not equal to NP. That said, there is this theoretical question that still remains. If somebody proves that satisfiability really is absolutely can't be done fast, then they've proven P is not equal to NP, and they're famous. If someone comes up with a fast algorithm for satisfiability, they prove P equals NP, and they're famous. Okay? I walk around life very comfortably believing that P is not equal to NP. But this is what the question is. Okay? Any questions about that? Any questions about the P equals NP or any of the consequences of this? Okay? Anything else on this? You get 1 minute left to ask questions in here. Yes? People say the world would end if P is equal to NP. Okay, the world would change if suppose, let's say, okay, there's a novel, by the way, if people want something to read.